that if a price is attainable, how to price it. And we know that if a derivative is not attainable, how to price it, or at least we are going to see that why this is the case. Okay? So let me draw a picture. Picture is this. Okay, so since I have such a model, I have S mod and it can be S from omega 1 till S from omega n. Okay? So consider S and V axis. Okay. Where S represent the discounted stock price. Okay. We should put S bar. For the sake of simplification, it's better to put S actually. Okay. Then at time 0, what is going to be the value of the stock? It's going to be S naught. Okay? And this S naught can be in future take one of these possibilities. Okay? What if I discount these stock prices? So discounting of these stock prices is going to give me what? Is going to give me, in each case of the scenario, each of the scenarios is going to give me the worth of it at time 0. That's not. So there should be S1 of S1 bar of omega n, which should be somewhere here, and there should be S1 bar of omega 1, it should be here at. Why these two guys should be there at? Because this is smaller and this is bigger. And then I can have different values of omega n minus 1 bar at that. S1 bar of now imagine at time 0 I have value S naught, but at time 1 that's the trajectory that the stock takes. Okay. Now your D, which also depends on omega, and hence depends on the scenario, okay, is going to take some value depending on S1 of omega. So I'm going to say that corresponding to S1 of omega 1, this derivative D is going to have some value. I don't know which value is going to be that. It is going to have some value. D of omega 1. In case of this, where D can be? It can be anywhere. Here maybe. You need to keep in mind, like this must be smaller than this, but it's not necessary that d bar of omega 2 must also be smaller than d bar of 1 actually. So you can have a more payoff in case when the stock goes down. You can have situations when more derivative is going to give you payoff if the stock goes down actually. So, okay. And similarly, this is also going to have a value a random picture. Could be other way around as well, doesn't matter. Okay. Now, I want a super replicating portfolio. Okay. So what that super replicating portfolio should do?
It should be greater than all.
It should be above all these points. It should be above all these points. Okay. You need to also keep in view so it should be above all these. So I can have many things above all these points. So these are the lines which are above all these points. If the value is anywhere, is going to. But we want to bring this line down actually as much as possible. That's what the infimum is doing. That's what the infimum is doing. The question is how to bring it down. The answer is that we can do so by looking at the value that I can compute of the portfolio that I can compute through S0. In other words, this V0 phi. V0 phi. Now try to draw a line which is above all points and hits this point. So that is going to be your the required, what do you call it, portfolio. That is going to allow you to compute the required super replicating portfolio, or maybe the ask price. So all you have to do is that try to draw a line. I can easily do it. Just think about it. I can easily do it. If I just take these 2 points in case of the picture, okay? So these are like, so I can have, so these are like, so these 2 points have kind of coordinates at S1 bar D, omega, S1 bar D, and bar omega. It's just in case of these. And try to draw in a straight line. Okay? Try to draw in a straight line. So wherever this straight line is going to hit, this is basically your something that is interesting. What we need to do is we need to draw something which is above all of these. Okay. What could be the potential equation of this line? The potential equation of this line is going to be xi plus s. These are like A and B. Okay. So that's like intercept, and that's what the slope of the line is. While V and S are like x and y. Coordinate geometry. Okay. So whatever I have described there, it's written there actually in theoretical form. I'm not writing it, I just shown you actually. Now what this line is going to do, this theta and xi is going to do, this b equal to theta plus xi is going to do, that in each of the case, S1 bar of omega, because what is S? S is S1 bar. It is always going to be bigger than E bar of omega, for all omega. Okay. So this is like what? So this is like your super applicating portfolio. That's easy. Where is your super applicating portfolio? Your super applicating portfolio is xi and eta. Okay, so the slope and intercept meaning here. You need to see that. Okay. Phi is super applicating portfolio. That is that this line lies above all of the points. The points, these points, S bar of omega I and D bar of omega I. Lies above all of the points. Okay. Now, as I said, this line is going to intersect with this line V equal to omega plus eta is going to intersect that. The point where the line intercepts the point. So that's one point. The other point is that this line V is going to intersect with S equal to S naught. Okay? And when it is going to, hit S equal to S naught, at that point what we are going to have? We are going to have V naught phi, which is xi eta, okay, and whose value is what?
By
A, or what do you call it? It's going to be xi plus eta S naught, because S equal to S naught is going to be this. And in order to find, so we kind of found one potential price, but that's not a good. So it's like we have this super applicating portfolio. We kind of found its value at time 0, but we don't just want this. We want least of such values. So what we need to do for that, roughly what we need to do, we need to bring down this line in such a way that it is above all points and hits this line somewhere. Okay? And the strategy to do so is that, okay, just choose two extreme points. Okay, something which is above all and something which is below all. Okay, for example, okay, if I just do it like that, okay, then just draw a line that passes through these 2 points. So when you draw a line which passes through the extreme points, so wherever this line is going to hit this S equal to, S naught line is going to be what you call the ask price. Without getting into the details, what do you think what we should do other way around? What should be the other way around? So for the bid price, what we need to do, we have to be below all of the points.
dw of n minus 1 sub.
Then what we need to do, then just think about it, okay, what is going to be the line which passes through, for example, two extreme points in such a way that that line is below all of these points, okay? And see that where this line hits basically. That's what you have to do. So when we can find eta, y and eta is replicating, super replicating portfolio in such a way that the value of this portfolio at time 0 is minimum. So that's what then we are going to say that okay, this portfolio with a minimum value in such a way that it super replicates all of the potential payoffs of the derivative is going to be what you call this value phi a is your super replicating portfolio. Okay, it's super replicating. I know it's a bit boring proof, but it's not that bad actually. Once you understand it, it's not that bad. You know what you are doing. Super replicating portfolio such that V naught of phi a is least then the pi a, the ask price should be this V naught of phi. Okay. And similarly, we can find phi b. Then to use what we need to do for the phi b. So we're going to have phi b. So it's a sub-replicating portfolio, just like a portfolio whose value always lies between or below basically all these points. Okay? And wherever it hits this V naught phi is going to be the fixed value. Okay? And that is going to be what you call the bid price. So phi b is sub-replicating portfolio such that at time 1 or at time 0, this is going to give me what you call the okay. Now that's the existence proof. We know every time such a thing exists. In other words, both of the such portfolios exist actually. Okay. So imagine I have lots of points. Okay. These are the values for the picture. Okay. S naught is somewhere here. So it takes. Then what we need to do in order to find the sub-replicating portfolio? So you have to choose those 2 points. Okay, which are. So you have to see the picture. Okay, what is given to you? Okay, you need to see the picture and try to find basically this line. Okay. So when you found this line, that's going to give you a portfolio, and then see that okay, what is the value of that portfolio when it intersects with this. And similarly, imagine that in this case, I'll choose these 2 points. So you can see this in examples. So for any number of points, these 2 points exist. Their existence is guaranteed. Okay, the only thing which remains is that show that any price in between is going to be the fair price. Okay? Obviously, pi b equal to pi b less than pi a also follows from, at least we can see it pictorially. Now, since I have, so that's next I would like to prove, this not here. Okay, so I'll just give you a sketch of it. So imagine I have phi A and phi B with me. Okay? Then I know that the value of B bar lies between what? It lies between value of phi B and
Pi.
A and 9. And as B is not attainable, so there exists some omega and omega prime in omega such that for which v1 phi b of omega is strictly less than d of omega and d bar of omega, d bar of d of omega, and v1 phi a of omega prime is strictly less than d of omega prime. So at least for one scenario this must happen, otherwise you can have equality. Okay. This is the case. Now, using this inequality, I'm incorporating this basically, I can come up with this, that if I, for example, apply conditional expectation, not conditional expectation, but expectation throughout the inequality, okay, I know that I can have EQ of V1 phi B less than or equal to or strictly less than EQ of, if I put bar, I need to put bar everywhere, less than EQ of V1 phi A bar. Okay, so I'm going to have this. Since my assumption is that my model is viable, so that's not a trouble. I have a discrete probability measure. Okay. The only thing that you can say that, okay, if the values have an order, why the expectations should have an order. Okay. It's an elementary thing that you can prove that if a random variable x has values bigger than y, then expectation of x should be bigger than expectation of y. Okay? So the hint for the proof is that consider this case when x is y, show that this implies that expectation of x must be greater than y. Use that to basically demonstrate this. Okay? So I can show this. So I can have, I know that all of these have non-negative values, so I'm safe. Okay. We should always justify things that we want. Why you should have a strict inequality? Because at least for 1 omega we have this item. Okay? So therefore, you are going to have a strict income. Then you see that why you should have a strict income. You know, you can have a situation, for example, when V1 of phi of omega is equal to D of omega in all cases. But there is one place where, you know, this is strictly smaller than this. Okay? So if you compute the expectation, you know, it's going to be, you know, going to be strictly smaller. So strictness is going to come inside. Now, if I have this, then I have, then this guy is what? This guy is what? So that's your phi b. This guy is your phi. Okay. And EQ of D bar is what? Is the fair price of the derivative. And know that this guy is a fair price of the derivative. So this inequality or this analysis shows that it should always be sitting between pi b and pi. Okay. So it proves that, okay, that's a good range for fair price. Okay. Last part of the proof you can do it for yourself. I'm not doing it. It basically shows that, okay, if anything goes beyond this, in other words, if this is above, you know, the ask price or below bid price, why you're going to have an arbitrage opportunity. Okay? So it just creates a portfolio and just, you know, shows that this is going to happen. Okay? So that's a rough sketch of it. And you can do this example, the next two example pricing of put option based on this approach. I would like to, so I'm not going to repeat all these calculations. I mean, you can read it for yourself. Okay. But I would like to point out one very important thing actually, which is very interesting. Alright, so let's move to the example. This example is same as the example we did in the start of the chapter. It's precisely same. So imagine that I have a model, okay, which is 3.5. There is 3.5. Here the evolution of equations. So I imagine this is 220, this is 230, 210, and this one is 290, okay, and R is 0.